Welcome to the next talk. Our next speaker is Johanna Barzen. She is a postdoc at the University of Stuttgart and she is running digital humanities projects as well as of now 2 quantum projects and from next month on 4 quantum projects. And the talk will be about quantum patterns and QHAna, so continuing, diving deeper into some aspects that we sketched at the very beginning. Johanna.
Thank you very much. So yes, it's a great pleasure to me to present our work on quantum patterns and QHAna. And I want to stress that it's our work, it's not me alone, it's teamwork, and we've got quite a big team, and a lot of the colleagues are here with me today who are working on quantum patterns and QHAna. Quantum patterns, so the talk has two main parts, we're a bit separated. The quantum patterns are more a bit on the theoretical side, so how can we provide best knowledge, so some application knowledge to people how to work with quantum computers, with quantum algorithms. And the second part, QHAna, is more to practically providing application knowledge on how we can interpret the results we're getting by quantum algorithms in this field, in quantum machine learning algorithms. And we are comparing the results from classical machine learning with quantum machine learning, and this is something you can do with QHAna. So starting with quantum patterns, we know patterns in many different areas. So originally coming from architecture, housing architecture, but we know in computer science there are many pattern languages for cloud computing, for integration, and so on. I did do my PhD on costume patterns, so from a very different area on, but why should we be interested in quantum computing patterns, or more precise, in quantum computing algorithm pattern? This is what we are talking about. Just as a short motivation, we've seen now in the talks before already, and we'll see in the whole day today, that quantum computing is an upcoming technology we need to be aware of. And we see very rapid development in the recent years. We already talked about access, so we can access different quantum hardware via the cloud, so they are publicly available already. And they're very different, I just named 3, very different impact we do expect, where quantum computers do provide a lot of potential. For example, for the combination optimization, so graph problems, scheduling problems, in chemistry, there's a lot of potential in design of materials or design of drugs. And what we will see in the second part of the talk in machine learning, like quantum neural networks, classification, clustering, so we'll dive in this deeper in the second part. And next to this, that is an upcoming technology, so that we need to be aware of it. It is a very heterogeneous field. So we got the physics, we got the mathematics, we got the computer scientists, and we need somehow some sort of common language between those different disciplines. And this is where patterns may help or be one instrument to provide knowledge across these different disciplines. And as we are working in quite a few research projects where industry is involved, we can see that in industry there's a very huge demand on education. And patterns, as they are nuggets of advice, of small items, they are good instrument, as education instrument for industry too. So this is why we are working on quantum computing patterns. Here you can see the format of these quantum computing patterns. So with quantum computing, our patterns at general are about is to make proven solution explicit. So we have many quantum algorithms out there. We have a lot of solutions, and we look at them. If there are significant elements, we can find quite often. So they are proven. They can be seen in different algorithms, in different applications. And then we abstract from these concrete solutions the actual solution, the abstract solution that is written down as a pattern. And the patterns always do have a certain name. They have an icon. The icon is always to remember very fast what is this pattern about. It has got a certain intent, because the patterns are always a solution, so we need to formulate which problem can be solved by this pattern. It has the solution, this is actually the heart of each pattern. It has got a solution sketch to make a very easy, very abstract way to communicate the core parts of each pattern. It has a result, so if you apply the pattern, you get something that actually resolves the problem you've got at hand. There can be variations, and patterns are not single islands, but the patterns are related to each other, so we've got relations, often semantic relations between the pattern, to compose a pattern language. So there are many patterns who are connected to each other, so you can start with one problem and then you probably need more than just one pattern to solve this problem. We have now seen already in the talk, I think in Frank talks, it was again how's the general structure of the quantum computing algorithm. So you have to think about some line in between. The lower part is the classical part, the upper part is the part that is going on the quantum computer. We've got the state preparation, this is our actual algorithm and the measurement. And we did already find quite a few patterns on different levels around this, the classical algorithm. And as I said, they are abstracted from concrete solutions. The patterns are not invented, the patterns are found. So you have to take a close look at what is out there to abstract the actual patterns. And we talked now a few times already that it's very hard to get the data into the quantum algorithms. So as you can see here, there are different patterns for preparing the state and data encoding to actually get the state to the circuits. So you can, of course, use some amplitude encoding or some angle encoding or some basic encoding. And all those encodings, of course, come with several costs. So sometimes you need a lot of qubits, sometimes you need a lot of gates, and this has some impact on the depth and the width of your circuit. So the patterns give you some advice for the problem at hand you've got to what is probably the best way to encode your data for an algorithm. The next part of pattern is about the unitary transformation. So these are patterns about things we found in quite a few algorithms. For example, the amplitude amplification is something that's known from the famous Grover algorithms, or we've heard quite a few times now already that we often have oracles in the algorithms. We have got program flow patterns that are actually a bit more on the so not only on the small part, but on a bigger scale, so about the whole algorithm. For example, we can take a look here for the VQA pattern, which is variation in quantum algorithms, and we can see the icon. As I said, the icons are always to give you a very quick idea of what the pattern is about. We've got a classical part, we've got a quantum part, and we've got a loop in between. This loop actually is always a classical optimization, and the parameters then are used in the quantum algorithm. So we are on this side now, a quantum state patterns we could find already, we could author already, like unitary transformation or creating entanglement. We know entanglement is one of the core items that we need to get an exponential speed up at quantum computing, so this is something we need very often in the algorithms. And last one we've talked about this now already in the talks before already too. We have noisy machines, so we need to cope with the noise in the machines we have today, so we need error handling pattern to address this problem with the machines. Nowadays we've got, and I just want to deep in one of the patterns a bit more closely, how does one of these patterns really look like? It's the error readout mitigation pattern. And here you can see the structure, as I had shown before, the format of each pattern, so you can see nicely it has an intent. The intent is how to reduce the impact of measurement errors. It has forces, so it has a little bit, why is it different to address this problem, or what are the forces we need to keep in mind? So we talked about that the machines have only low decoherence times. The measurements are not very precise. We've got only a small number of qubits, so we need to keep this in mind. This is why it's probably very difficult to address it. And the solution is then to apply this error readout mitigation method, which improves the resulted quality based on the observed measurement characteristics. And I said the core of every pattern is a solution sketch. This is what we can see down here now. So we got a circuit, we do run the circuit on a machine. What we get is a noisy measurement. Here we need to apply the readout error mitigation to improve the results. How can we do this? This can we see in the example section. So we need to create this calibration matrix that Benjamin just showed to us already, and we do apply it on the noisy measurement to get better results, and this is what the results section tells us. So what can we achieve by applying the pattern? We get a more precise probability distribution at the cost of a classical post-processing. So this is how these patterns look like, and if you're interested in working with the patterns, there were quite a few references on papers where you can find the long version, but a short version to just take a look at it and get to it is here at quantumcomputingpatterns.org, where you can see the icons, and when you go to the patterns you can get more information if you're interested in working with them. We at the Institute are not only working in providing those patterns by finding them, authoring them in pattern format, but we're also working on how can we provide them for people who want to work with them in a best and optimal way. So those of you who have been here the last years, we have presented our pattern atlas, which was our pattern repository we did build over the last years with the costume pattern and the cloud computing. There was a lot of going on with pattern atlas, but when we tried to build this, we always run into the problem that it's not enough to just have a website where the patterns are. So we need to think about how can we interconnect pattern languages, because of many problems it's not enough to just go to one pattern language. We need patterns from other pattern languages, and this is why we came up with the idea of the pattern atlas. This is like it's like thinking of the different pattern languages we got being on the surface of a new globe. So we got the cloud computing patterns, the integration patterns, and the security patterns, and they are a bit like maps on a globe of the total IT domain. So based on this idea, we did think a little bit about the analogy it has. So the pattern language can be seen as maps of geographic regions. So, and the links in between of the pattern languages are like the arrangements on the maps on the total globe. And the views, we need special views, because if you just look at all the pattern languages, of course, it's far too much. So you need to think about which patterns actually are useful for your problem. So you need a view on only these patterns. This is what special representation of regions can be. We need not only the pattern languages, but we often connect them to the solutions we have found. So it's more like them again. So the solutions are like concrete renderings of the map. And we need some entry points. So where can we start? And this is what we know as index in an atlas. And of course, we need to glue those pattern languages together to have a good understanding of a certain problem area. And this is, here we can see the pattern atlas as tooling for interconnected patterns. So you can see here there are different patterns on the side. And very nicely can be seen that these are patterns, the gray and black and white ones are from one pattern languages. The green ones we can see are from a different pattern language already. There are interconnections that are between the pattern languages, so you can get a view that actually addresses exactly the problem area and all the different patterns we need from the different pattern languages together, so that you can nicely address your problem. I will stop with the patterns here and go over to QHAna at this point. And it's quite a hard cut, I know, but I wanted to start with the several parts we've got. QHAna is for Quantum Humanities Analysis Tool. I will talk a very short time about quantum humanities and what is our idea of quantum humanities, and come then to an analysis tool, so how did we implement the idea in this field. So the quantum humanities started off, I think, 2 or 3 years ago. We see in the humanities that we got an establishment of the digital humanities. So using classical computers to address problems in the humanities. And we know now already from the talks before, quantum computers are not only becoming real, they are real already, not at the scale as we want them, but they are real and they are there. We need to be aware. And the quantum humanities idea, or the vision, is actually quite simple. It's going beyond classical computing in humanities too, coming to to quantum computing too. So in a very simplified way, when you look at the history, how research is done in the humanities, the core part, the cultural basis of humanities is hermeneutic. So interpreting certain artifacts, and this is mainly done by someone who's analyzing these artifacts, thinking about them, trying to provide some explanations. With the digital humanities, we now have tools, we have opportunities to ask much bigger questions. So if we go to Google Books and make a database search, we can ask very different questions than we could do. So it's not only reading one book, or we can have a look at a whole pile of books now and ask different questions that are allowed because of the tools we have. And, of course, the idea of quantum humanities going on, so steps further, we've got this new potential, very powerful machines, and we need to think where can we use them in the humanities too. And as it is very different, as we've seen in the other talks already, working with these machines, it's worth giving it a name, and this is what we try to do with quantum humanities. Why should we use a quantum computer in the humanities? Also, this is a very simplified way to point to all the core elements of potential we can expect by quantum computers. And we have to say again, it's just about the ideal quantum computer. This is not where we are yet. This is something we can expect later on. And we have heard today a few times already that they can solve problems much faster than classical computer. Maybe this is not too interesting for the humanities, as they have not that many data at the moment, but it's always good to be faster. They enable the processing of large amounts of data in a single step, and they promise, and this is where we are with QHAna, they promise a higher degree of accuracy in certain algorithms. And this is where we are in the machine learning area, where we come with the QHAna tool later on, again, to this point. They solve problem classes which are practically not solvable so far, so we need to think about where in humanities maybe this can help too. And this is always a bit hard, there are problems that can only be solved on quantum computers. So this is something, of course, we need to think. Maybe there are new ways where we need to address problems with this capability you get by these new machines. And they used to be, at least expected, this is also not where we are today, as they're quite expensive, but they are expected to be much cheaper than using supercomputers. And everyone knows that the humanities are always quite stained in the financing, so this would be a very nice point. And they promise to be more energy efficient. This is also not core part of the humanities, but as we are in energy crisis and in climate change, I think even if they're not faster, even if they're not more precise, it's worth getting ready to use this technology if it is really more energy efficient. So, as I said, this is not where we are, and we will hear much more of this with machine when Marie is talking later on, so I will skip this a little bit and come from the potentials a little bit to the challenges. So, of course, there are a lot of challenges when wanting to apply quantum computer to the humanities. So from the application side, of course, we need to think about what are actually suitable problems that can be addressed, which we talked about the problem of finding a common language in a heterogeneous field. This is much worse when humanists come into account, of course. This is more, it's a very different culture of thinking again. We need to think about which algorithms can be used, how can we cope with categorical data, as most of the algorithms need numerical data. In the humanities, we've got a lot of categorical data. From quantum computer side, of course, we've heard many of the problems that are there already. We need to talk about data preparation. We've seen in Benjamin's talk that expanding the oracles often means a lot of new gates that need to be applied. We need better connectivity between the qubits so that we can actually use entanglement, and entanglement always is the basis for making algorithms faster. So read error mitigation, we've talked about that enough for today. So there are a lot of open points we need to think about to really get into a good solution. But what we wanted to do is to just start with a very down-to-earth use case at the beginning, to have an application, to have one use case from the digital humanities where we use quantum computer to have a look if it's really worth using it already. And the use case is from our project, from our digital humanities project, Muse. And Muse is, and I said about, at the beginning, I'm working on costume pattern languages. So Muse is about finding costume pattern language. So it's about, it has got a lot of data on which materials, which colors, which designs are used in special films to communicate a certain character or to communicate a certain stereotype. So we got here down there the Muse database where all those data about costumes are stored. And we did analyze those data with classical analytic tools at the beginning, and we now wanted to apply quantum computing machine learning algorithm too. So the very abstract overall process, what we are doing is we of course need to do some feature extraction on, because we've got very many data, and the data has very many features. So we do find a proper feature space, actually proper in the sense of as low dimensional as possible, of course, to map the data to a feature space, so we can run some clustering algorithms to find those costumes that can be grouped together to have the same effect. For example, what kind of clothes do we need to communicate a sheriff? You need a sheriff star and a sheriff hat, and we want to find some cluster that actually contains the costumes, for example, for a certain stereotype. And we want to do some classification, so after we found the cluster, we need to find the right hyperplanes in between, so that new clothes that are captured on a daily basis, so we're still capturing costume data, that they are mapped right away to the right cluster, so that they can be mapped to the right pattern in our thinking. And on several steps, we can use already quantum-based algorithms. And this is what we want to show with QHAna now. Going one step further, we of course do use the very normal, or we can see in many projects, this is not due to the costumes, of course, the way on how to analyze data. So we got at the beginning some data cleansing, which contains the data acquisition, format convention, how to treat missing values, data repair, and so on. We got the data preparation, and this is more the classical data preparation, not the preparation for the quantum computing circuits then. So we need to talk about, we need to think about how is our data structured, is it possible to process this data with the algorithms. What sort of encoding do we want? Maybe we use just one-hot encoding, or do we need to reduce our features by feature selection, feature extraction? So we need to think about the data, of course. We then need to do an algorithm selection, so we need to determine in the family of algorithms, do we need a classification or a clustering or a regression, the proper family of algorithms to then get the proper member. So if you do a clustering, do I need a max cut or a k-mean? So there are a lot of different clustering algorithms out there, and then I need a choice on the hyperparameters that have a lot of impact on the results, of course. To then execute the algorithm and to make some result evaluation. Very often, if you can't do build a hypothesis based on the results, you have to go back again to try a new algorithm. If you have a new algorithm, you often have to go back to the data preparation. So it looks very straightforward here. It is not when doing analysis of data. So this is a quite cumbersome process to build a hypothesis and then to validate the hypothesis. What we are doing in the next step, again, is based on the hypothesis. Of course, we want to find pattern candidates, in my case, costume patterns, but this can be abstracted from the patterns, from the costume as well, to create a whole pattern language. When we have the pattern candidates, we can verify them as patterns, and we need a pattern relation to get a total pattern language at the end. So in our tool QHAna, we did focus on 4 of the main steps of this pipeline I just showed. So we focus on the data preparation, feature engineering, clustering, and classification. And here we can see a screenshot of the main menu of QHAna. So we got some documentation at the beginning. It's just providing all the information, which libraries we are using, which papers we are using, so that there is a documentation which information we are relying on, and we've got at the end an overview. This is where all the different results are shown from the intermediate steps, so that we can compare the different results. And the data preparation, feature and clustering classification, of course, can be done by different algorithms, as I've presented before already. So I can use, for example, as data preparation, just a normal one-hot encoding, or what we are doing, and I will deep into this a bit more in detail later on, the distance space computation. And many of the algorithms, for example, the max-cut algorithm is there in different implementations. We've got different classical implementation and quantum-based implementation, so we can really have a look at the results, have a look at what happens when we have different hyperparameters, so we can just play a little bit with these different algorithms. So now going a bit more deeper in distance space computation, this is what we are using to get the categorical data I got from the costumes into numerical data. So here it's very small, I know, it's just a taxonomy on colors. So at the costumes we have got all the parameters we do need to describe the costume in total. We have the values structured as taxonomies. And here you can't see, but you could see, if it is a bit bigger, that we have like dark green, light green, yellow, blue. And we are using this Palmer similarity to give each value we have down here some similarity measure to another value. So we can say, based on the Palmer metric, and this is just substituting them into the formula, we get very nice values that reflect the dark blue and light blue is very close to each other, while dark blue and yellow is very far from each other. So we can extract, based on the taxonomy, a similarity value of all the attributes used to describe a costume. So we get just one single value describing the distance from the y and the x, for example. And of course, in costume, it's a bit more complex, as we've got one costume and the second costume, costume A, costume B, and each costume has got a color which is structured as a taxonomy, has design that is structured as a taxonomy, has material for so we have to build the similarity measures between the different colors. We have to build the mean, and again we have to do this for all the other attributes and build the mean value between the different attributes to get just one single similarity measure between the two costumes we have got. And but at the end we only have got one single data to describe the distance between the different costumes. And what we get then when using the data preparation, we can see very nicely, we can choose which of the attributes we want to look at, how are they compared, how do we build the mean, what are we doing with empty slices. We can get such distance metrics, so similarity measures can be easily transferred to distance metrics, and this is then our numerical data based on the categorical data we did start off with. We can see here the result of 25 costumes, just the color and the genre values, and we can see in the middle line, the blue, each costume, like costume 24, and costume 24 is to itself, it's the maximum similarity we can reach, but the red costumes are not similar at all. So if you go to costume 1 and costume 9 is quite similar, while costume 1 and costume 11 is not similar at all. So this is what we can reach by the Palmer metric. Based on this, we can go to the feature engineering step and just choose some embedding. So in our case, we choose the MDS embedding, the multi-dimensional scaling embedding, and we can here choose the hyperparameter for the algorithm. So for example, in this case, we have just 2 dimensions. We want to press the data in a 2-dimensional space, and this is what we can see here. We again got this the costume with the color and genre values. So here we go, and just 2-dimensional, we can see the different costumes mapped to this space. As I said, QHAna is about comparison. So it's just one way I just presented how we can get these distance measurements, but of course there are different ways to getting them. And what we also did is using a hybrid autoencoder. So hybrid means we have a classical autoencoder and then a quantum-based autoencoder that are interconnected. And we use this to also produce distance measures. And we can see here very nicely, we've got the same 10 costumes in both of the pictures. And in the middle again, we've got each costume similarity to each other. And we can see nicely that the first 5 costumes are quite close to each other in both ways, even if this is a statistical way to reach the distance measure, and this is the Palmer-made way, so that we can see in very different ways to reach quite similar results. That we have got those costumes are close together, the other costumes down here, so costume 5 to costume 9 is very, very different from each other. The quantum autoencoder, just again, this is very small, but you don't need to read the detail. The quantum autoencoder, here you can see what the quantum autoencoder, for example, does. So we have an input preparation at the beginning, we then got the encoder, we have then a resetting of 2 of the 4 qubits we are using to 0, so all the compressed data is in these other 2 qubits, and we've got a decoder that actually tries to again to find the input data based on just the compressed data in here, and then we have a measurement. We need, of course, the first part is the training. You can see there are quite a few, we need qubits, we need a lot of gates, and this is also, I showed it very small. So this is actually exactly the part I don't want to show in QHAna. You can see it's quite complex, and this is something a humanist is not interested in. You're just interested in the results. So this is what QHAna actually is abstracted of. So what we can see in QHAna only is we have different algorithms. Each of the algorithms, if I choose one of these algorithms, has certain parameters. I can change those parameters, and then I can go also back now in the clustering step, and we can see that there are quite a few different clustering algorithms in there already. I can go back, choose a different one, and I don't need to bother about all the circuits in behind or the gates in behind. I can just go for it without needing to know all the detailed information. So here we can see some of the results. Again, we've got 10 costumes, which are in a multi-dimensional scaling, which is in a 2-dimensional space. And we have got different max-cut implementations here. So we've got this one is just a classical max-cut, this one is classical max-cut 2, this one is a quantum-based max-cut. And when we look at the data in this picture, we can see that we actually expect on this side the 5 costumes to be a cluster, and we do expect, if we use at least a distance space clustering algorithm, we would expect that this on the other side we have some cluster 2. And when we look at the classical results, or the results of the classical max-cut implementation, this is actually exactly what we get. So we've got a cluster on the left and the right side. The quantum-based max-cut doesn't do it at all. So we're not very happy with these results. And what we can then do in QHAna is, as I said before, we can of course try a bit, if we can improve the results by getting better by using different hyperparameters. In this case, we just increased the maximal trial of the optimizer, and as you can see very nicely, we started with 1, with 50, 100, and 150. Then we get very nicely to the good results we reached with the classical algorithms. And this is not as it's not so stunning when you're just doing it with 10 costumes, but it gives you something at hand if you have a bigger use case, how to choose the parameters for your algorithm that you can get at least as good results as in the classical implementation. But this is, when you do comparison, of course, you don't get always the results you like, and in this case you can say, maybe it's better using the classical algorithm, so the quantum is not as good yet. We did this with other algorithms. Here's a k-means algorithm, just as a quick result where we can see that the classical max-cut and the quantum-based k-means, not max-cut anymore, has quite similar results, which is good. But where it gets a bit more interesting is in the classification. So what I said before already, what's classification about? We have clusters already, and we want to try to find a hyperplane that separates the classes. And Of course, if I have, in this case, linear separable data, it's not too hard. There are different ways I can put a hyperplane in between, but if I now try to classify a new object, we've got a new object here, the black one, for example, it gets classified as the green triangles. In this case, I can't be classified. Only in this case, it gets classified as one of the blue circles. So finding the right hyperplane, in this case, actually, in terms of finding the biggest margin on both sides between the classes, so that new elements can be classified too. It gets a bit more complicated, of course, when we have non-linear separable data. In this case, there's no way where I can just put a line in between to separate them, so I do somehow need to apply a trick. For example, in this case here, I can apply a new dimension. This is what we here have with the z-axis. I do apply a new dimension that reflects the distance from the origin. So I've got my y and x just pressed down here, and the new dimension that reflects this distance, and I can then add again an hyperplane in between, calculated back because of the circle function. And adding this new dimension, or putting this data in a very high dimensional feature space, this is something where quantum computers are really, really good at. So this is why we especially hope that in this field we can get better results. And what we did is, again, we are now in the classification part. We implemented some classical, some quantum-based support vector machines that we made mainly, and we can see here some results. This is a classical support vector machine, this is a quantum-based support vector machine, again on 40 costumes, and the costumes are classified negative and positive, so the purple ones are negative, the red ones are positive, and we are now trying to find ideal lines in between to separate them. And interesting is up here, so we can see with the classical support vector machine on this data set, we only reached 72% of accuracy, while with the quantum kernel estimation that you can see on the other side, we actually reached 90%. So now we have to be fair. When we started with the clustering before, we of course tried to optimize it by the hyperparameters, which is the same in this case, and we also did try different kernel functions and change the hyperparameters, and we got better. We got to 81% with the classical support vector machine, but it's still, we didn't reach the results we could reach with the quantum kernel estimation. But of course, this is just one use case. We had, on this data set, we got this good result. It needs much more investigation if this really stands in other use cases too. So summing up a little bit the goals of QHAna as I presented it, it is a tool where we try, for at least me, to find, of course, pattern candidates for my use case. But beyond this use case, it's a tool independent of the presented use case is, of course, the usage to have data and try to find out which algorithms are a good way to analyze this data is far beyond the costume domain of interest. So it's about comparing results of classical quantum-based algorithms, but also, and I'm not sure if you've seen it in the parameters, also different backends. We have not only the IBM implementations. So we want to, of course, have, and this is what's written here, a tool that has this analysis pipeline with integrates very heterogeneous tools, so you can have them very easy access without having to know all the special details. And this, of course, for me, it's an evaluation of the potential for quantum humanities in a bigger scope. I would just give a very glimpse on the outlook. As I said, it's not costume specific, so we want to make it very generic. And this is what colleagues at the Institute are working on. We are now building, we are rebuilding QHAna totally as a plugin-based architecture where you can just find all the different algorithms as plugins, and you can then put them together with different in the way you do need to analyze your data. You can put your own data here, so it's very easy then to adapt it, to get to use it for other use cases too. I will stop with a short outlook where are we standing on both the parts I did present. So we got the quantum computing patterns at the beginning. What are we doing with the patterns? Of course, we need to work a bit more to provide more patterns, but we are also trying to integrate them in our big project Planck, so that we've got a lot of people who are working with the patterns. Patterns are not they are not ready at a certain point. You always need to rework with them. You always have to see if they are new state-of-the-art, especially in quantum computing. There's a lot going on, so you always have to rethink them if they're still at the state-of-the-art. And of course, what we still need to do is to develop a corresponding solution language, because to really apply the pattern, it's very good to have also the concrete solution, which makes it not simpler to address the problems. And in the QHAna part down here, of course, we just started off. There are much more algorithms out there that need to be integrated, for sure. And we've seen today already that workflow is very promising in the area of quantum computing, so we need those plugins to be also integrated in the workflow, so we need to render all the algorithms expressed at the eye so that they are evocable from the workflows. There's a lot of work still to be done, but I wanted to present some first results in the area, and this is where I would stop for any questions, if there are any questions, and just wanted to remember that we have to go to the picture later on.
First of all, thank you very much. Thank you. Christian.
Well, I can try to speak loud. So I have a question regarding the late show. Because you stated correctly that digital humanities means that you're not starting to do some quantitative aspects, actually qualitative research. By, analyzing and coming up with numbers and extracting. Is that right?
Digital humanities is quite established in the last years, and yes, they are trying to make to find ways to help the hermeneutics by giving some results that are actually reproducible, that are reliable. And yes, with the quantum computer, we bring again with the distribution, we bring again some items, but. I think, and I'm not sure if this is true, but what I think is maybe we can use this quantum computer states, for example, to encode this insecurity we have in many things in the humanities. Maybe this is an interesting part where we can bring together the quality of quantum computer with the problems we have in the humanities. So we should give it a try.
Yeah, now the comment. I remember when the design patterns came out and how much it helped people understanding object orientation and applying safe, bulletproof designs. And I can think that this is a very good start for starting community, exploring and trying to identify stable design. So this was like a very promising approach. And now the late joke. In Western, people always wear white hats, at least the good ones, so I guess this was a very good choice.
So next year we've got the stars.
Thank you. Are there further questions?
So collecting the programming patterns, I think that's very helpful. But what would also be helpful is to collect all those tricks in, for instance, how to encode something smartly as a Kubo formula and what to avoid. Because there seems to be a lot of experience out there, but I don't find it captured anywhere.
Yeah, and this is exactly what we want to do with the patterns. So we do want to, I just showed very quickly that we want to connect those patterns to concrete solutions. So this is what is done in the example or in the known user section of each pattern, where you can connect it to very concrete ways. And in our project Planck, I think Michael will show later on, there are much more, the patterns are just one way of presenting this knowledge. And it's connected to quite a lot of application knowledge we get from this project, where a lot of different companies are providing use cases. So it's far beyond just the abstracted solution we have in the patterns. Of course, you do need for real application, building real application, more than just, can be seen as a very good education and entry point to solve a problem, but of course then we need some more specific information.
Because there are all those tricks out there. I'm squaring this because, and if you only look at the formula, there's no way to understand why people go through those, jump through those hoops. Yeah.
Thank you. Is there another question? If not, thanks again, Johanna. Thank you. So we meet outside for the group picture. See you. And then we reconvene at 2 o'clock. Is it 2 o'clock? Yeah, okay, 2 o'clock.
Yeah.